Now in this lecture we will do some observations on left cosets and right cosets. So let us come to the observations. So number 1. Recall in the example V4 we have taken H to be a subgroup EA. Then what will happen is that if we consider AH, then AH is equal to H is equal to EH, we have seen it. But if we take BH, then BH will be, we have two elements B and C. So as it is clear from here that it is not a subgroup of V4 because identity element is not here. So coset either left or right need not be subgroup. Why I am saying need not be, because this is also a coset but it is the subgroup H, and this is also a coset which is not a subgroup. So coset need not be a subgroup. Second observation, suppose G is a group, H is its subgroup, and I take an element A in G. Then if you will write AH, then AH has elements of the form AH such that H is in H. But because H is a subgroup, so identity element will be inside H. So an element A can be written as A into E. And as you can see that A into E is of this form, A into E, because E belongs to H. So it means A belongs to AH. So this is the fact that A always belongs to the coset AH. A always belongs to the coset AH. Now come to the next observation, observation number 3. Now, so take an element A in G implies A belongs to H, where H is a subgroup of the group G. So take any element A in G, that element will belong to its coset. So it simply means that this A belongs to union of all the cosets A in G. So we can change the notation here because I am using all the cosets, so B and BH. So what does it mean? Take any element A in G, A will be inside this union, so it simply implies that G is contained inside BH. But each of the coset is actually a subset of union B in G. But each of the coset is a subset of G, but BH is a subset of G for all B in G. So this simply means that union BH, B belongs to G, is contained in G. So from this and this it is clear that G is equal to the union of BH such that this is equal to the union of BH such that B belongs to G. So the group G is union of the cosets of H. So this is actually the left coset. The same thing we can do with the right coset. So for right coset, if you will do, so you have G is the union of HB, B belongs to G. So it is also true for right coset. So whatever we are saying, it is also true for right coset. This is also true for right coset. This is also true for right coset. So G can be written as a union of left cosets, or G can be written as a union of right cosets. Now come to the next observation, observation number 4. Now suppose an element A belongs to H, where H is a subgroup of a group G. Then what will happen is that for any H in H, AH, this element is of H, this element is also of H, and when you will compose, because H is a subgroup, so the composition will also be in H. So for any H in H, AH is in H. So this simply means that the set AH such that H is in H is contained in H if A belongs to H. So it means the coset AH, it means the coset AH is contained in H. Now further take any element H in H, then what will happen is that H can be written as, so then H can be written as A inverse H. We can write it like this. So I take one element H in H, then H can be written like this. But A is in H, so A inverse is also in H. So A inverse H is in H. So this element belongs to AH. This simply means that for each H in H, H will belongs to AH. So it means H is contained in AH. So by these two, hence, what is the conclusion? A belongs to H implies AH is equal to H. So if A is an element of capital H, then AH is equal to H. Now, the same thing we can do for right coset also. Now, conversely, suppose AH is equal to H. Then as we have seen just now in the observation that A always belongs to H. So this implies A belongs to AH, which is equal to H. So A belongs to H. So it means if AH is equal to H, then A belongs to H, and if A is in H, then AH is equal to H. So this thing can be rewritten as A belongs to H if and only if AH is equal to H. Now if we will extend it and do the same thing for right coset also, then we can also write here HA. The same thing is true for right cosets. So A is in H if and only if the coset determined by A is same as H. Now come to the fifth observation. Observation number 5. So suppose I take two elements, take AB in G such that AH intersection BH is not equal to phi. AH intersection BH is not equal to phi. So what will happen is that take one element which is in both the coset. So take an element C in AH intersection BH. Take an element C in AH intersection BH. So how this C will look like? This implies this C will be, because it is in AH, so it will be some A times H1, where H1 is an element of capital H, and it will also be look like B times some elements H2, where H1 H2 belongs to H. This simply means that A can be written as, if you see on this, A can be written as B times H2 H1, or B can be written as A times H1 H2 inverse. This implies A belongs to BH. And in fact it is not or, but it is and. And B belongs to AH. Now if A belongs to BH, then this also implies that if we will multiply some elements from right side AH, because A is already in BH, so AH, how will this AH will look like? You will multiply H here and H here, so it will again of this form BH, so it will also belongs to BH. And similarly, if you will multiply H in B, then small h, this belongs to AH. And this is true for all H. This is true for all H. So it means that AH is contained in BH, and simultaneously BH is contained in AH. So this simply means that AH is equal to BH. So if AH intersection BH is not equal to phi, then it means that AH is equal to BH. So let me write it again. AH intersection BH is not equal to phi implies AH is equal to BH. Now if AH is equal to BH, then intersection will also be non-empty because both are equal, so intersection will be whole thing. So we can write it as if and only if. So this is our observation. This is our observation that AH intersection BH is not equal to phi if and only if AH is equal to BH. Now logically, negative of this is equivalent to negative of this. So what is negative of this? AH is not equal to BH if and only if the negative of this is AH intersection BH is equal to phi. What does it mean? It means that if two cosets are not equal, then they are disjoint. There is nothing common in between them.